Hi, students. How are you? Oh, sad. Yeah, you saw a substitute and figured, ooh, free period today. Woo, this is going to be a fun day. I'm glad Mr. Bessling's sick. Boy, I've never been. No, you guys weren't thinking that. But you know me, you guys are AP students. I would never miss an opportunity for you guys to learn, would I? No, and this is yet another great opportunity for you all to learn. So I'm going to finish just about 9.1 today. I'm not going to expect you guys are experts, but you should be by Monday because you're going to have a quiz on section 9.1. Aren't you excited? Who said that? Get him out of here. No, I'm kidding. I'm kidding. Nobody said that. Okay, so when we left off on Tuesday, we were looking at null and alternative hypotheses. Excuse me, this was on Monday. We had our test on Tuesday. We were looking, I kind of ran through this basketball example that I made this pretty bold claim that I shoot 80% free throws. You guys, even though you've watched my trash get ball and you're pretty impressed with my trash get ball, you think that I'm actually maybe overestimating my abilities, which is a nice way of saying you guys think I don't really shoot 80%. So we did this in the notes, but let's go ahead and write H naught, the null hypothesis, and H1, the alternative. And we already did this, so I'm just going to move to the next slide. And again, we said the null was that P equals 0.8. And the alternative is P is less than 0.8. And we need to define our parameter. So what do you mean by P? Where P is the true proportion of free throws made by Mr. Bessling. I just realized too, when we say define parameters, with these hypothesis tests, we always are looking at parameters. We want to make some generalization about the whole population in this case. You'll see in your homework tonight, this is why we don't say p hat equals 0.8. P hat is from a sample. There's no reason to make any inference on a sample. There's reason to make inference on a population. Okay, so I think this is kind of where we had left off. So suppose in an effort to test this claim, I take 83 free throws and I end up making 54 of them. Of those 83. It's not bad. This is the bigger assumption, but let's assume it right now anyway, that each shot's independent. That is, that if I really shoot 80%, that even though by shot number 70 something I'm getting pretty tired, I still have a 80% chance of making it. Hold on, I gotta pause. Again, that's normally a bigger assumption, but I'm telling you all to make it. So, okay, so again, this is the idea of a hypothesis test. I make this claim, you're going to test this claim, whether it's true or not, and I make 54 out of 83. Again, that's not bad. I don't think that's 80%, is it? So how likely is a result this low or lower if I really do shoot 80%? We can answer this question. So again, if I really shoot 80%, what's the probability of me making 54 out of 83 or less? And to do this, we're going to use what we learned in Chapter 7, the sampling distribution of P hat. Right, if the conditions are met. So random, okay, is a little bit of an assumption, but we're going to assume this is taking a free throw is a random chance event. Independent, again, we were told to assume that. This is the part that I still have to finish. So we want to use the normal distribution to approximate this binomial event. So is NP and N1 minus P greater than 10. And in this case, for P, we're going to use 0.8, the actual parameter. So 83 times 0.8. That's a decimal in there. Is that greater than 10? And then 83 times 0.2, the probability of me missing a free throw. Is that greater than 10? Well, I got to get on my computer and get my calculator here. So 83 times 0.8 0.8, thank you very much. Not comma 8, I can't see. 66.4. Last time I checked, 66.4 is greater than 10. And 83 times 0.2 should be the remainder, 16.6, which is greater than 10 as well. So that means we could use a normal approximation. And I wrote a few things here. What's my statistic? My statistic was p hat in this case, where I made 54 out of 83. So this is my free throw percentage in this trial, in this particular trial. And I made, oh wow, just right about 65.1% of my free throws. Not quite 80%, is it, like I claimed? So the answer is, could this have happened by random chance? You know, I really shoot 80%, but just, well, let's answer this. Excuse me. How likely is this to have occurred by random chance? Because we definitely know it's lower. But, hey, if it was just one of my bad 20 or 30% of the days, there's not strong evidence to show that I shoot less than 80%. But maybe if this is extremely unlikely to happen, then there's actually a lot of evidence against my claim now, right? Okay, the mean of my statistic, again, we're looking at p hat. That is, if I really shoot 80%, how many shots would you expect me to make out of 83.8? And we did that calculation above already in the normal part, NP. It was 66.4. Excuse me. It's my first day. It's not my first day. This is, gotta erase this. This is for a binomial event. Sorry, I've been teaching this in regular stats class, so it's not NP. You guys remember what this is? The mean of P is the mean of P hat. That is, again, if I really shoot 80% over and over, what's my average free throws percentage? Well, 80%, right? Excuse me on that. Standard deviation of the statistic. This is our sigma of P hat. And again, this isn't the standard error. This is the actual sampling distribution, standard deviation under the null hypothesis if the null hypothesis is true. So this is our square root of P times the square root of 1 minus P all over N. So I'm trying to get a number for that right now. N was 83, and I got 0.044. 0.04. Yeah, I'll just round it to 3 decimal places right now. Okay, so what does that all mean? I don't know. Just kidding. Of course I know. That means if it's true that I really shoot 80%, that if I were to take multiple samples of this, that is multiple trials over and over and over, I take 83 shots, I always shoot 80%, then this is the distribution of, you could think, my free throw percentage for every sample, for p hat, the proportion of shots that I made. So it's got a mean of 0.8, a standard deviation of 0.043, and what I'm interested in is, since in my particular sample I ended up shooting 54 out of 83, which was 65.1%, what is the probability that I actually make this low or lower? Well, I got everything I need now. Let's just take a z-score. So it's going to be my observed value minus the mean of the distribution divided by the standard deviation. I got 0.651. I got to put that in parentheses. 0.651 minus 0.8 divided by 0.043, and I got a z-score of, whoa, I say that because that's bad. It's making me look bad. Pretty darn low z-score of negative 3.46. So now what I want to do is find the probability that I get a sample this low or lower. So the probability that my sample mean was less than 0.651, taking our z-score, that's going to be equivalent that our z-score is less than 3.046. And if you use one of the tables, that's going to be less than 0.001 or 0.1%. But I'm going to look I'm going to put this on my computer, see if I can get a more precise number, if I'm using the right code. Yeah, I got almost exactly that. 0.0010, almost exactly. So essentially, okay, let's do this. What do you think about my claim now? Do I really shoot 80%? Or do I shoot lower than 80%? Well, given that this was a good sample, it was random, it was independent, the probability of me shooting this less or less, or shooting this low or less, is 0.1%. That's extremely improbable to happen by random chance. It would be much more likely, be much more safe to say that I probably shoot less than 80%. I was probably, lying the whole time. Not that I would do that. In reality, I'd probably be stoked if I did shoot 65%. I shoot probably reality 40-50% at best, but that's when I used to try. Okay, what we just calculated is a p-value. And this is exactly what a p-value is. A p-value is the probability of a result from a sample being this extreme, brought to you by Monster Energy Drink, or more extreme, brought to you by Monster Energy Drink, if the null hypothesis is true. That was really awkward. All right, so this is the p-value is one big thing in statistics, and I hear this from so many teachers. I miss Mr. Empting. He always used to be, "What's your p-value? What's your p-value on that?" I'm looking at my black cat right now. "Hey, kitty, what's your p-value?" And the truth is that most people don't really understand what a p-value is. A p-value is, again, it's the probability of observing a result this extreme or more extreme, and I'm going to underline this. This is a big condition here. If the null hypothesis is true. Okay, there's some more precise definitions of p-values, but this one is going to be just fantastic for our class. If the null hypothesis is true, the probability of me, or let me rephrase what we just did. If I really shot 80%, which is if the null hypothesis is true, then the probability of me shooting this low or lower at 65.1%, out of 83 shots, is 0.001. Very unlikely. Okay. So low p-values are indicators that our results are unlikely to occur if the null hypothesis is true, thus providing evidence against the null hypothesis in favor of the alternative. So we're going to end up pretty much making decisions using these p-values. But before we make these decisions, so we're kind of going, the decision is essentially going to be null hypothesis yay, alternative nay, or null hypothesis nay, alternative yay. But before we get there, we got to ask ourselves how low of a p-value is too low. Well, we're going to need to set something that we call the significance level alpha. And your book uses another definition. You're going to get really used to this idea of alpha. I'll show you a different definition tomorrow about alpha. But alpha is essentially, we're going to call it the cutoff point for our p-value. So it's kind of like how low is too low. And the most common values for alpha, pretty much the only ones we'll be using, is 10%, 0.10, 5%, 0.05, or 1%, 0.01. What to set it at, we're going to look at in a little bit. You might want to go, just set it as low as you can, but there's going to be some consequences to that as well. We'll see in a little bit. Okay, so we're going to call the significance level alpha the cutoff point for our p-value, and we're going to use that cutoff point to make a decision. So our decision is going to be rather binary. And when I say binary, it's either this or that. Here's our decisions. If our p-value is bigger than our significance level alpha, we fail to reject the null hypothesis. We have not found enough evidence against the null hypothesis. Just hypothetically, had I shot maybe something like 75% in that last sample, maybe the probability of me shooting 70% or 75% or less ended up maybe being about a 30% chance. In that case, 30% is higher than even a traditional level of alpha. That you wouldn't have enough evidence to say that I didn't shoot 80% if I shot 83 shots and made 75% of those, because it could easily, there's a 30% chance a result like that could have happened by random chance if I really still shot 80%. So it wouldn't give you enough evidence. But if our p-value is low, like I said, we're going to reject the null in favor of the alternative. Now I want to throw out some words here. I use my words carefully. Notice how if the p-value is greater than alpha, I didn't accept the null hypothesis, did I? I mentioned the other day that these hypothesis tests are very much like our criminal justice system. We don't find people innocent, right? We find them not guilty. So our assumption is they didn't do it. Then we look at all the evidence, and we ultimately have to make some kind of judgment based on the evidence. And we always know that our decision we could be slightly wrong in our decisions, right? Unfortunately, it happens. But the idea of, you could kind of think that if the p-value is big, it's kind of like, hey, the probability that, let's say, somebody's on trial, that the probability that this person didn't do it isn't low enough for me to say, to call them out on it. So I'd find them not guilty, not innocent. For instance, even in my basketball shot, if I did make 75% of my shots, that doesn't mean I do shoot 80%, right? I could shoot 79%. I could shoot 75%, had an average day. I could really shoot 70% and just have had a good day. Who knows? My real lifetime free throw percentage could have been 60%, and I just had a phenomenal day, and I got lucky. So there's a lot of things that could have happened that we don't necessarily know. So last part of this, decisions. What could possibly go wrong? Wrong. Yeah, I know. It's funny. It's funny, I know. We have decisions, and we have reality, usually unknown. Like I was mentioning, we're gonna make some kind of decision based on an unknown reality, and who knows what reality is? Somebody knows, but it's not me. So let's look at what could possibly go wrong. Okay, so I'm going to make oops, I missed something in my chart here. We're going to make a little chart here. So on the top, we have our decisions, and on the rows here, we're going to have reality. So our decisions, this is all possible outcomes of a hypothesis test. Our decisions, we could either reject the null hypothesis or fail to reject the null hypothesis. But in reality, the null hypothesis could have been true, or the null hypothesis could have been false. If we were, let's start with good stuff. Okay, let's say the null hypothesis is true, and we ended up not rejecting the null hypothesis. That's correct, right? That we did. I was about to write good, but I'm going to write we made the correct decision. If the null was really true, and we failed to reject it. Or, if we rejected the null hypothesis and the null hypothesis was really false, we also made the correct decision. For instance, just again throwing out the criminal justice system, so think about rejecting as like finding someone guilty, and failing to reject as finding them not guilty. And then maybe in reality they either were not guilty or they were guilty. It's kind of like, all right, if I just found somebody not guilty and they really were not guilty, I pat myself on the back, I made the correct decision. Poor person who had to go through that, right? Or if I find the person guilty and he really was guilty, same thing. I pat myself on the back. I made the correct decision. I am hopefully, making society a little bit better place by, making someone pay for their crimes and keeping them away from society to commit other crimes. That's just fantastic. But what happens if I find somebody guilty and they were really not guilty? Yikes. Or in hypothesis testing terms, that's rejecting the null hypothesis when the null hypothesis was actually true. This is a type 1 error. For instance, in the basketball case, our p-value was essentially 0.0010, which was way lower than our significance level, even though we hadn't set it yet. It was still lower than 1%. So I would have rejected the null hypothesis, but maybe I really had a horrible day, whatever it was, just complete random chance. That's literally a 1 in 1,000 event, and you just happen to be in that 1 in 1,000 event right then. That's a type 1 error. As you can see, 1 in 1,000, not very likely, which is why we stick with our decision, right? Or we could have not rejected my claim, when in reality, my claim was actually true. Let me do that again. We could have failed to reject the null hypothesis when in reality the null hypothesis was false. So this would be like finding somebody not guilty of a crime when in reality they did it. And that kind of stinks too, right? You don't want to let a criminal go scot-free, right? Well, that's what we call a type 2 error. And in the basketball case, a type 2 error would have been maybe one of those situations I was talking about earlier, that maybe, so 65, I shot 65% of my sample, but let's pretend I shot 75%. And again, we're testing the claim that I shoot 80%, and we just didn't, at 75%, let's hypothetically say the p-value was 0.3 or 30%, and we would have come to the conclusion that we didn't have enough evidence to call shenanigans on my claim. But maybe in reality, as I said, I actually shoot 70% and just had a particularly good day. Well, we would have made a type 2 error then. So to formalize a type 1 error, and we also usually call this number alpha, that same alpha that you saw from the significance level, because alpha literally represents the probability of committing a type 1 error. When in a type 1 error, again, is when we reject the null hypothesis when the null hypothesis is true. And beta is when we fail to reject the null hypothesis when the null hypothesis was really false, and that's the Greek letter beta. So going back to that significance level and alpha, when we're setting alpha, we're really kind of asking ourselves, how likely would I be to commit a type 1 error? Literally, if our alpha was 10%, then there's a 10% chance of committing a type 1 error. Again, like if we did my basketball example, for instance, I'll draw it out here, and we said that I shot 80% on average. I'm not exactly sure what this cutoff is, although we could use our z-scores and an inverse norm to find it. There's some percentage where every single time if I shot lower than this percentage, let's just say it's 70%, you would have rejected my claim. And again, that would happen by random chance in 1 out of 10 samples, 10%. Beta, however, we can't really calculate that well easily. We won't worry about calculating beta because it gets complicated. But beta is when we fail to reject the null hypothesis when it's really false. And again, that would happen just by chance. Sorry, I'm losing it. Okay, so the idea is to consider the consequences of both type 1 and type 2 errors when setting alpha. If you really want to avoid committing it, so the idea is you have a situation, you have a null and alternative hypothesis, and you ask yourself, what's a type 1 error? What's a type 2 error in this case? And which is worse, or are they just about the same? So if committing a type 1 error is really bad, then use a low alpha level at 1%, because essentially now there's a 1% chance of committing a type 1 error. If a type 2 error, I'm sorry, just going back to a type setting your alpha, if a type 1 error is worse, you don't want to reject the null when it was really true. So by setting it at 1%, you're essentially just going to be, even if you were to do this over and over and over, rejecting, if the null hypothesis was really true, you'd only reject 1% of all possible samples. But if a type 2 error is worse, if the consequence of committing a type 2 error is worse, you want to use a higher level of alpha. You're going to be rejecting the null hypothesis more often, 10% of the time versus 1% of the time. Again, if you were to repeat these processes over and over and over and repeated sampling, if you will. If type 2 error is worse, then use 10%, because you're essentially going to be, let's say, failing to reject the null hypothesis more often. Less often. We'll get there in a second, guys. My brain's going. If they're about equal, like if this is usually the more common level of alpha, use 5% significance level of alpha. Okay, I'm going to just try one problem out of your book. If I could get my cat off my book. Beat it, kitty. Meow. This is out of your homework. I'm just going to read this to you. Number 24. Blood pressure screening. Your company markets a computerized device for detecting high blood pressure. The device measures an individual blood pressure once per hour at randomly selected times throughout a 12-hour period. Then it calculates the mean systolic blood pressure for the sample of measurements. Based on the sample results, the device determines whether there is convincing evidence that the individual's actual mean systolic blood pressure is greater than 130. If so, it recommends that the patient seeks medical attention. Okay, so part A asks to set a null and alternative hypothesis. So, the idea again was that if your blood this is randomly once an hour going to measure your blood pressure. If your systolic blood pressure is over 130, it's going to tell you that you need help, to put it in layman's terms. So the null is, we're just going to assume the mean blood pressure is 130 versus the alternative that we kind of want to show that it's greater than 130. And again, we want to define our parameter where mu is the mean, I'm going to call it the true mean blood pressure, systolic blood pressure of its users, this machine. Okay, part B asks to describe a type 1, type 2 error and explain which is worse. Or explain the consequence of each, and then I'll throw on there which one's worse and what should you set the significance level on. Okay, so let's go. Type 1 error. Type 1 error is rejecting the null when it's true. So what that means in this case is that you would that the machine would tell you your blood pressure is over 130 when it really wasn't. What happens if it's over 130? It's going to go tell you to go get help, but you really didn't need help. So it's kind of like a false positive. All right, that would stink. You have to go all the way to the doctor. You're like, but doctor, this says I've got high blood pressure. He's like, no, you're fine. Type 2 error. What's type 2 error? Well, type 2 error would be not rejecting the null when it was false, when essentially the alternative was true. So what does that mean? That means the machine's telling you that your blood pressure is fine at 130, but in reality, it's higher. Uh-oh, that's trouble, isn't it? That means you might really need medical help, medical assistance when, indeed sorry, let me do that. Yeah, you would have needed medical assistance, yet your machine's not telling you. That to me is way worse, right? I mean, who knows? You could die from that. So, given that, what would you want to set the machine at? Well, I would significance level. Anybody want to answer that? Yeah, you in the back? No, not you. The person next to you. Yeah, good job. 10%. Yeah. And again, you're gonna, in this case, you're gonna be making a few more false positives, sending people to the hospital when they didn't when they didn't need to, or I don't want to say sending to the hospital, but they're trying to get help when they didn't need to. But all in all, you're at least going to be minimizing the type 2 errors in this case. Alright, see, that was like a half an hour lesson, and with all of that, you're ready for your quiz on Monday. Kitty, anything you want to add to that? He's not in a talking mood. He just ate his breakfast, and he sees a bird he wants to eat. Okay. All right, guys. I hope that was a good, informative lesson, and if you need to hear it again, the good news, read your book, and this will be up on YouTube. I'll put a link on it. So, cool. All right. Have a good rest of the day. I'll see you guys tomorrow. Sorry I'm not with you today. Okay. Bye.